Goal is simple today, but I want to get a bunch of things out of this. But I want to start with the most basic part of this, and this is to study the motion of the harmonic oscillator. To do so, I want to kind of go back to first semester and kind of remind you that if you start with something like say a ramp, we know that this object will have an acceleration that's a constant, right? And it'll just slide down the ramp. But with that idea that it has an acceleration that's constant, because a equals dv dt, well, then we can say that the velocity is going to be equal to at plus v naught. This is something we did first semester. We take the antiderivative of a with respect to t and produce a function. And this gave me the velocity of the box as a function of time, using v naught as our boundary condition. And then if I want to know position, well, I just take the antiderivative of this function, because x is v is dx dt. So if I want to figure out where the object is, take the antiderivative again. And we have created a set of motion equations that describe where the object is and how fast it's going at any time. We did that for things that had constant velocity. So we did first semester. And although we didn't derive it just like this, we started with algebra because that was something that you all had in common. You now should be able to do this using calculus. This is the reason why we studied kinematics first and then immediately talked about net force. If you're really trying to understand physics, net force still has all the same properties, all the same specifics that we were dealing with earlier, but it allows us to recognize that if you know the forces acting on your object, you should be able to come up with position and velocity by taking whatever your net force is and replacing A with dv dt. And build yourself a velocity as a function of time formula. And then, of course, wherever you see velocity, replace it with dx dt. And make a new differential equation, take some calculus, and produce a position function. And that's what we're going to do today. We're going to try to. We're going to try to do that with the spring mass oscillator. And I want to just take a look at two situations. This is the at-rest situation. The object is at equilibrium, and because it's at equilibrium, there's no motion. I have not added any energy to the system. This is considered a stable equilibrium, and the reason is because it's a spring, and we know from a spring that the force from a spring is equal to minus kx. Now, I want to remind you of that from first semester, but this negative sign is kind of critical to this. It's what produces a stable equilibrium. What that means is if I move the object away from equilibrium, I will immediately create a force that will try to push the object back towards equilibrium. The spring pulls the object back to the equilibrium position. That might not sound like much, but consider the alternative if that negative sign didn't exist. So if I have a bowl and I put a marble in the bowl, if I put it at equilibrium, it'll just sit there at the bottom of the bowl, right? No big deal. But if I move the marble to the side, will there exist a force that will cause the object to go back to equilibrium? Yeah, this looks a lot like a restoring force. Now, that's because this force is in the opposite direction of the displacement. If I change this, turn the bowl upside down, I have an equilibrium position. I can place the marble at the top of the bowl. But the moment I displace the marble, will there be a force to push it back towards equilibrium? No, I create a force, all right, but this force is in the same direction that my displacement was in. And so this force will exist to push the marble away from equilibrium. That makes this an unstable equilibrium. We don't build buildings with unstable equilibriums, because if we did, the moment they were slightly displaced, they'd fall apart. We build buildings with stable equilibriums. So when the wind blows on them and hits them, they might get displaced some, but there will be a force that will push them back to equilibrium. Does that make sense? Again, another way we study and deal with simple harmonic motion. So although Hooke's law doesn't seem like a big deal, that negative sign makes a lot of difference in what it is we're studying. But if we want to come up with a motion equation to describe the motion of our object, then we need to take our net force and set it equal to ma. In this case, the only force acting on the object is going to be the spring, which means we'll have minus kx equal to ma. Now, when we did this a minute ago, we had a net force equation that equaled a constant. So finding the antiderivative was pretty easy. If we try to find the motion equation here by dropping in our derivative, I think we have a problem. And I don't know if you see the problem already, but we have x in here, but we don't have anything that has t. And let's be honest, this isn't a constant, right? This is going to change as the position changes. Moreover, we know that v is equal to dx dt, so we could write this as m times d dt of dx dt. Now, this is a differential equation. It's got x on one side, a differential that has to do with x, and it's got x on the other side, where the actual object is. This is something we could work with, except that there's two derivatives there and not one. And because there's two derivatives there, I don't know that I can use the rules that we have so far. And we only have a couple rules, right? We have the polynomial rules, and that's about it. And these won't fit the polynomial rules. So I'm going to have to show you a different way to deal with this. And by the way, you guys who are even in calculus, you don't cover this in calculus. This would be something you would cover in your first differential equations class. And so we're going to do chapter 1 of your first differential equations class. And you're going to love this. This is kind of fun. I expect that you know where this came from and everything till here. I expect you know that and can reproduce that. What we're going to do next, I want you to know the results. If you end up not knowing the result, if you end up not knowing the process to get there, that's fine. But I want you to know the results, okay? Raise your hand if you're in calculus. See, that's a lot of you, so I can expect great things from this room. The first thing I want to do is I do want to show you a little bit of symbology. Because this is the derivative of the derivative, we write this as like this. It looks kind of silly, but we say the d's are squared and the bottom is squared, and we write that as a second derivative. So that makes this a second order differential equation. The order tells you what level of derivative that you have. It's kind of like the order of a polynomial, so, but slightly different. I'm still going to do what we talked about before when we dealt with separation of variables, but we can't do separation of variables here because it's a second derivative. But we can solve this for the differential portion of the function. And when we do, we're stuck with this. Now, this might not seem like something you can understand, but I think you can understand it better than you think. Remember, out there somewhere is x as a function of t. That it exists out there. Just like first semester, we had an x as a function of t. This is x as a function of t. So we've had this function before. We've had functions that describe an object's motion. So we know there's got to be a function out there that describes the motion of our simple harmonic oscillator. This says that if I take the derivative twice, I will get the original function back, a constant, and a negative sign. So instead of using like some fancy process to figure out what the function is, we're going to do chapter 1 of differential equations. We're going to guess. We are going to make up a function. Can you, who have calculus, think of a function that when you take the derivative gives you back the original function? Go ahead. E to the x. I'm going to do it instead of e to the x, I'm going to do it e to the t. Is that okay? So I need to have an x naught out here or something to represent what the initial position of the object is. And then I'll have e to the t. I am just creating a function. Now, if I want to take the derivative, I can. dx dt, this would be the velocity. I can take the derivative of this function. And what is the derivative of e to the t with respect to t? E to the t. Yep. Excellent. So I get back my original function. That's great. If I take the derivative again, I'll get the second derivative with respect to t. And this is just the acceleration, but again, I'm taking the derivative of what I just did. I'm going to get the same thing. This does not match that because I didn't get any variable out of it. So I need to change this or modify this so I can start getting something that will pop out a variable. So how about I put a c here? What will my first derivative be? Go ahead.
X naught c e to
Yeah, this will pop out a c, won't it? If that c is here and that c is here, oh, it won't pop it out there, it'll pop it out down there. If I take the derivative again, it'll pop it out again, right? So I'll have a c squared here. So that produces a constant, right? That constant could be k over m, but it doesn't produce a negative sign. We need to produce a negative sign. You might be thinking, put a negative sign here, but will that work? No, so it'll pop it out the first time, sure, but then the second time I'll have a negative times a negative, and that'll go away. Now, everybody who has calculus knows that this was never going to work. All right, like I said, I steered you here kind of on purpose, but I want to find a guess that's more realistic. So let's consider a guess that's more realistic. And just as a reminder, we're looking at a system like this. Now, I can't do this side to side like we did in class. We're going to look at it up and down. But if that's equilibrium, we start by giving our object, a small amount of displacement, and we set it into motion, right? You already did this lab, so you know what this looks like. This is no big deal. And I won't let this thing stay here very long, because some of you can't stop staring at it and will turn yourselves half asleep because you get so easily hypnotized, because you are very susceptible to suggestion. So just take a look, and that's enough. If we're trying to build a function that we believe can satisfy this parameter here, because this is the parameter we want to satisfy. And just a reminder, this parameter says that if we take the derivative of our function twice, that's this side. If we take the derivative of our function twice, we get back the same function we had at the very start, but we also have a constant and a negative sign. So those things have to occur for our system. So we're going to choose a different function besides the exponential. Which one do you think we should use? Go ahead. Cosine or sine. We have to pick one of those, because either one is going to work. Which one makes the most relevant sense here? Go ahead.
Cosine.
Why?
Because the derivative gives you a negative.
Well, true, but we're taking two derivatives. We're going to get that negative one way or the other. If we start with sine, our derivative will give us cosine, and then, of course, our second derivative will give us the negative sign that we need for the final step. Remember, we have two derivatives to do. So we can pick either one, and we're eventually going to get that negative sign, correct? The question is, which one fits our model best, cosine or sine? Yeah?
Would be sine.
Why?
Because it could be, because it's modeled by a sine function. The normal motion would be modeled by a sine function, and it would have like a negative
let's do this, because I think something's being missed, probably because we had a day in between. Let's do both. And then at the end, we'll pick the one that fits our system best. Is that okay for you guys? So we're going to look at two sets. We'll look at the sine of some constant. Now I'm going to use a c here, but that's temporary because I used the c yesterday. Is that okay? So this will be temporary because that's not a good symbol to use. But we're also going to have the cosine. Now, this can't be all we have here because sine produces a number between 1 and -1 and has no units when we're done here. So we need something out front that represents position. So I'm going to put an x0 out front because this is going to represent what I did to the object. I gave the object an initial displacement. And if you monitored your work enough, you know that unless something was happening, the object moved back and forth between the same displacement above and the same displacement below. So I'm using x0 to represent that initial displacement. I'm going to use it on both. Because remember, we have to have an x here that represents the motion of the object, where the object is. So I think this is going to be a position, a location. Good so far? So we have two different ways to do this. Our first one is to produce the velocity, which is dx dt. So we're going to do that in both places. All of you are right. If I take the derivative of sine, what do I get? Cosine. That's right. Now, unfortunately, that's not sufficient because I also have to take the derivative of what's inside here using something called the chain rule. So I know some of you don't have the calculus experience, and so you're learning it. But when you do the chain rule, you apply the derivative to the function first, but then we have to apply the derivative again to what's inside this partial portion of the function, the argument. And so when we take the derivative of ct with respect to c, with respect to t, we get a c out front. So I'm going to put it over here because when you do the chain rule, you kind of chain the things together, but we'll reorient that in a minute. Now, when I take the derivative of cosine, what's the derivative of cosine? Negative sine. So I am going to get this negative out front. We were hoping for that, and I have sine now of ct. But again, we're going to take the chain rule, and that's going to give us another value for c. All good? Any questions about that? Okay. Got to do it again to get the second derivative. This is going to give us the part that's about acceleration. This is why we're doing this, because of Newton's law. So start on the left side. We're going to take the derivative of cosine. We already know the answer. It's going to be minus sine. So I'll have my x0 here, and I'll have the minus sign out front, and then I'll have sine of ct. But then I'll have another c, which is going to give me c squared. And I'll take the derivative of sine here on the other side. My negative sign is going to stay here. My x0 is going to stay here. But I'm going to get cosine again, ct, and I'll have a c squared here. Now, both of these functions match our goal. Again, our goal is to show that if you have the second derivative of our function, you get a minus sign, you get a constant, and you get the function. So when we compare just this one with this one, I'm saying this is my function, and I see that function right here. Right? I also see a constant, and I see a negative sign. I have all the parameters I need. This fits exactly what my second derivative tells me it should fit. But this one does too. I have my function that I had originally. I have a constant, and I have a negative sign. So both of these are solutions to our differential equation. Now again, this process of finding a solution to a differential equation by guessing, not particularly efficient, as you can imagine. The more complicated this is, the more difficult it would ever be to guess at an answer, which is why, because either one of these answers fits what's up there, which of these is better for our circumstance? Now, if you don't know why I'm asking that, there's a reason to choose cosine or sine. We have to pick which of these actually represents our function. And either is okay, because if you look at your actual lab data, can you tell which one of these is sine and which one of these is cosine? But you know from experience how the cosine function differs from the sine function. Can you tell me how the cosine function differs from the sine function? Go ahead.
Cosine, with the start of the function at 0, it starts on 1, but sine starts at 0.
Everybody good? So with that knowledge, which of these is better for what we did in the lab? Did we start our oscillator at 0, or do we start our oscillator at 1? Again, I am not trying to be tricky. That's equilibrium. That's 0. Did you start timing it from here? No. We pulled it down. This is our initial displacement, x naught, and we started timing it from there. We didn't capture that. That's why we don't have these starting at 1 or starting at whatever our displacement is. But what we did to get this started was give the object a certain displacement first and release it. So for our experience, cosine works better for position than sine, because it represents how we start an oscillator into motion. We give it an initial displacement, and then it begins oscillating thereafter. Does that make sense? That's why I think we should choose cosine. But both of these model our motion, because our object, we don't care about the start so much, do we? This thing is going to oscillate for a long period of time, and because of that, we can be anywhere within the function. And you guys already know that the only real difference between cosine and sine is a phase shift of 90, right? So, or pi over 2. So you guys understand it doesn't really matter which one we choose, and I don't really care which one we choose, except I'm going to go forward saying that our motion equation starts with cosine. So our position function will be the cosine function. So let's together here. First, this whole thing started because we created a differential equation. I have to keep emphasizing this. This differential equation has a certain look to it, like that. Right? This came directly from having a Hooke's law force that was unbalanced in our equation. Right? I'm being very careful here because this situation is particular. If you have a single force that acts on your object that can be modeled as a constant times a displacement, if you can do that, you will create a differential equation that looks like this. And there is a single useful solution to that differential equation. Now, technically, the constant that we put there should be the square root of k over m times t. And I say that because if you looked at what we had just a minute ago, we had a c squared there, right? So we're saying that this is our constant. If we follow this to the end, v, which is dx dt, is going to be minus x naught times the square root of k over m times the sine of the square root of k over m times t. Take the derivative again, we get acceleration equals minus x naught k over m cosine. The derivative of the cosine of square root of k over m times t. So I'm trying to say this so you understand the important parts. I don't care if you know where these came from. What I need you to know is that these are the direct result of solving this differential equation. And that means any force that is proportional to displacement will oscillate. If you can find any force where the force is proportional to the displacement, your system oscillates. So that's why this is valid. I mean, any time there's just any force that acts on a system that is proportional to your displacement, you will get simple harmonic motion. And these are the motion equations that go with it. Now, these motion equations are of limited use, ultimately. it's very seldom you're going to be asked, well, how fast is the object going after 12 seconds? Well, you could be. You could put 12 in for t, and it'll tell you how fast the object is going after 12 seconds. You understand what I'm saying here? But there are some important details here that I think you will miss out on if you're not paying super close attention. First, we understand that this portion of our function always goes between 1 and -1, right? It can never be bigger than that, which means this part out front represents the maximum of the function. Do you follow what I'm saying? Because these are always oscillating between 1 and -1. This tells you the fastest the object will ever go. This tells you the biggest the acceleration will ever be, and this tells you the farthest the object will ever go from equilibrium. So you have another consequence here that's not obvious, but needs to be made obvious. First, V max is going to be x naught times the root of k over m. That will have to be true, because that's the max of the function. And A max is always going to be x naught times k over m. Now this part I hope you get, but I don't know. We know this function repeats. When does it repeat? What has to happen inside here for our function to repeat? When you're dealing with sine and cosine, when does it go back to 0? Or when does it go back to 1? Every 2 pi, right? These systems repeat when what's inside there has increased by 2 pi. So if I want to figure out how long it takes for our system to oscillate, I can just set this equal to 2 pi. And if I do so, solve this for t, this represents how long it would take my system to oscillate. We call that the period of oscillation. It's just a consequence of understanding how the cosine and sine function work. Are we all good so far? All right. Now, this is probably worth having all of this information collected in one place. I'm going to add a couple little things to it. For example, sometimes things oscillate fast, and dealing with their period, which might be a fraction of a second, might be harder to do. So we also use the term frequency, which is the inverse of period. Just another term. But frequency is in oscillations per second, while period is in seconds per oscillation. So they're just inverses of each other. As a detail here, this is going to be in inverse seconds. And we have a name for this unit called the hertz. So things that oscillate fast, we tend to express their frequency. And things that oscillate slow, we tend to express their period. So something like the Earth going around the sun, we'd probably use period to describe that, because it doesn't make very many oscillations per second. But like a hummingbird's wings, we'd probably use frequency to describe that, because it does many flaps per second. You follow what I'm saying? So they're the same measurement. They're telling you the same information. We just tend to use this for things that go quickly and this for things that do go slowly. So clocks will use period, because they're going to have a period of like a second. But the frequency at which your microprocessor oscillates, well, that's probably in gigahertz. So we'll probably use frequency for that rather than period. All good so far? Okay. Here's where I'm going to flip this a bit. This is for the spring mass oscillator. However, there are lots of things that oscillate. So we're going to write these out as generic functions, because it should be clear to you that the k over m part of this is the thing that matters. It controls the function. But doesn't it appear in a lot of places over there, the square root of k over m? So we're going to define something called the angular frequency. We're going to use omega for it again. And we're going to replace all of these square root k over m with a generic placeholder called the angular frequency. I'm just erasing them. If I were you, I would probably just rewrite them. But I have through the magic of iPad, I'm just going to erase them all and then put omega here. And you might wonder why we use omega, but I'll be really clear about why we use omega in a second after you guys have rewritten that out. Omega is a term we already know. That's in radians per second. Omega is a term we already know. That's in radians per second. Since everything inside that parenthesis has to be in radians, we write this as omega because omega times t needs to be in radians. So that's why we list that as the angular frequency. All right. I'll show you